Okay, let's talk about chapter 1, where you do not do any calculations. You don't put any numbers in. You don't use math. What you do is you become aware of physics and you set up the physics problem. And this is often not given enough time. We say to do it, but the text jumps to the equations, and your professor often jumps to the equations because there's so much to do. There's just not time. But we need training in this. So chapter 1 is a critical chapter. And it's something that we will build on and use and use. So you may not be perfectly comfortable with chapter 1 right now, but do the exercises, struggle through it, compare with each other, make corrections, and then you'll be able to lay it out. You see, we're doing puzzles. And in this study of physics, your introduction to physics, we study simple motion and then we build up to more complex motion. But in so doing, you study the key to the scientific revolution, this really profound thing of being able to say that things move according to laws and we can track that. And so we can predict what's going to happen. Granted, first in simple situations, but then more complicated situations. So it's really cool. What's the key here? Yes, you're going to do some math, but the math comes out of it. So we're doing these puzzles. You don't dump the puzzle pieces and then just look at the puzzle pieces and solve it in your head. You just move it around, and it doesn't matter which puzzle piece you move around. So we're going to describe in words a process, and something as simple as throwing something up or dropping something. So first, one dimension: vertical, away from the floor, toward the floor, or horizontal, parallel to the floor, or along the floor, or desktop, along a ramp, up and down some ramp surface. All that's one dimensional, right? Now, north, south, east, and west, those directions are all horizontal, but we might draw them like this, right? But north is not that way. Can't get to Canada that way. Okay, so let's start describing this motion. You need 3 elements. So let's talk about this. What's the name of that? That's called kinematics, like cinema, moving pictures, right? Describing motion, kinesiology, kinetics, any of those words, that comes from the root of motion or describing motion. We're not saying why things move the way they do. That comes in chapter 7 and 8, which I really encourage you to get to. That's going to be a huge preparation for you. So chapter 1 is to visualize the process, the motion, someone walking, whatever, sketch it, and label it. 3 things are going to be needed in that. We're going to talk about that. Well, remember, we're just describing the motion. That alone is quite challenging, and you'll confront some hidden, unconscious misconceptions. Okay, they're common, so you can expect to have them because people do. So we're going to work through that. What do you need on your sketch? You need to show states of interest. So think of it as a movie, and you're going to hit pause. You can hit pause at each of the places in the movie that you want to find out things about. And we'll see what you would want to find out about those states. And we're going to pause at places that you know things about, right? That's the puzzle. You'll know some things and you'll find out other things. Okay, so in some ways it's simpler than it might seem, but we build on this in your physics class. The trouble initially is that you're learning new physics, but you're also learning a new way of thinking and laying things out. How to be a good problem solver. To be a good problem solver, you lay out what you have and you ask, what do I know? Not what don't I know? I don't know what this puzzle is. I lost the box. I just have the pieces. I don't know what this puzzle picture is, because that's a little kind of hard, right? That'd be a hard puzzle, like, the picture to look at. I don't know what it is. I'll just have to see what it is. Okay, so you lay out the puzzle piece and you ask yourself, what do I know? Because when you lay out what you know, you can get to the end product. So what do we need? We need to do the states or instance, the places where you pause. We need well subscripted variables. And I've created, which might seem like a simple thing. It's not, it's a huge thing. It will train your mind. Okay, I've created some notation here, earlier and later, and earlier to later. We're going to talk about that. And then you need to show your choice of which way is plus. Is plus up? If plus up is, if you choose plus up, then down is negative. But you can choose down to be plus and up is negative, right? Left can be positive, right can be negative. Right can be positive, left can be negative. It doesn't matter. All you have to be is consistent. We have to break free of the idea that that's positive. That can be positive, right? And that freedom is very, just so you know, it's no small thing. It's a huge thing, actually, because we can get into spherical coordinates and polar coordinates, you might have heard, and cylindrical coordinates, and they're very useful and they make things easier to think about and easier to calculate and easier to program. Okay, so what do we have? We're going to, the places where we pause and we have information or want information, we will subscript information that we need to describe motion. And then we will choose consciously and show which way is plus and consequently the other way is minus. Okay. And there's no right answer, but good coordinates we're going to see will help us to calculate more effectively, like I say, visualize, understand the motion, the results, the math more effectively, and maybe even program a computer more effectively. All right, so what do we need to put on these? Okay, here's the big blah. I was going to write it out for you, and this computer screen is creating a bit of a glare right there, but I'll compensate for that. So this is what you need to know. This is it. And what we're going to do, let's look at that good labeling. Okay. We're going to look at what I call states or instants, the places where you pause the video and find information about or have information about. Now, here's the new notation, which you don't see in books yet: time earlier and time later. So we've got an instant where you pause, and then an interval that is between any of those two places. And they don't have to be one after the other, sequential. It could be one, pause, 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 maybe between these two, any earlier and any later, and between earlier and later. All right, so here's the notation. This is going to pay off and it will train your thinking. It's, again, no small thing. Be disciplined and the payoff will be huge. So the time earlier, lowercase t, use good notation. There are some times where it's flexible. In this case, not capital T, lowercase t, subscript capital E. That's my notation earlier. Time later. You know the movie goes in one direction. So earlier to later, and so on. Now, when you apply it, so I put these into general equations, and we're going to build up using these in general. But when you apply it, then you have to say, oh, I mean time 1 to time 2, or time 1 to time 3, or time 2 to time 3. So earlier isn't just time 1. Earlier could be time 2, and then time 3, or time 4. Okay, so any earlier, so there are these general relations that will work between any earlier time and any later time. And that's going to be really great because then you get the hang of it. So the change in time is the Greek letter delta, the capital delta for change, the triangle there. The change in time from an earlier state, any earlier one, to any later one. What that means, now sometimes you'll just know what that is and sometimes you'll calculate it. So there's going to be multiple ways of doing it. You're going to have to know your tools, when to use which tool. So you can't just go to sleep and no one's going to tell you, just do this and you're going to paint by numbers. That's what one of the things that makes this hard, is that you're going to have to actually think about what tools do I use. But if you need, you can say the time from an earlier state to a later is the later time minus an earlier. Let's say that the earlier time was 2 seconds and the later time was 10 seconds after you started your stopwatch. Some earlier time was 2 seconds after you started the stopwatch, another was 10. Well, you could do it in your head. The time between those two states is 10 minus 2 or 8 seconds, of course. So that makes sense. Again, this would be for a general equation. And then when you apply it, you're going to specifically say, oh, I want to know the time between state 1 and 3 or 1 and 2. You can't go 3 to 1 because that's going backwards. We won't go into that. So that's all that is. Now, this idea of an instant is confusing to people. And it's unconsciously confusing. In fact, oftentimes people teaching it don't realize how much this vexes people. You see, when you pause a video, someone could be looking like this, right? And you don't know if they're just posing or they're actually running. Because when you pause a video, they could be moving, right? They could be moving, but they can't move in that instant. So in an instant, you can be changing, but you can't change because you pause the video. That's what that instant means, pause, right? It can be changing, but it can't change. That's more interesting than you might realize. And then there are positions. So space, here's time, here's space. Now positions. We label, again, be careful with the letters, get used to them. For position, we use X, we use Y, or we use Z. If it's 3 dimensions, we use X, Y, and Z. 2 dimensions, any two, usually X and Y. 1 dimension, X or Y, it depends. Okay. We often use Y for a vertical position, how high above the ground, or how low, right? A vertical, often, but that's okay. For horizontal, north, east, south, west. Those are all horizontal, right? We might draw it on the board like this, but that's not north, okay? Then we often use Y for north and south, X for east and west. So those are some conventions, fine, but you're free to use whichever. Now, if we're talking about 1 dimension, X earlier and X later, those could go into a general equation or relationship. But when I'm going to apply them specifically, and when I draw my picture, I'm going to label them X1, X2, X3. And the later one could be, so the earlier could be X2. Even though there's an X1, when I apply it, I might go, well, from X3 to X4, or from X2 to X3, or X2 to X4, X1 to X2, X1 to X3, X1 to X4. So you can relate any of those points, right? Any of those instants. And these are the positions in whatever units. You can use inches, you can use centimeters. Inches like that much. A centimeter is probably about that width, okay? So know that, okay? And 10 centimeters is like that, 4 inches, something like that. So get to know those things. You can use miles, you can use kilometers, you can use meters, you can use nanometers. There's a lot of different units for the position. If you use Y, then just replace the X with Y. If you have 2 dimensions, then you'll have X position and a Y, X earlier and Y earlier, X later, Y later. Okay, you'll get used to that. And generally we work up with 1 dimension first, but I throw in some early on. Displacement is the change in position. I'm going to clarify, that's tricky. You'll get the hang of it though. How do you get the hang of something? Don't just sit there and stare at it, use it, right? You can't stare at a basketball and get good shooting free throws. You got to use it. So too, do the exercises. So the change in position from any earlier state to any later in general is the later minus the earlier. Okay. Then when I apply it, a general relationship, you put in 1 to 3 is 3 minus 1, right? X3 minus X1, or 1 to 2. It's got to be earlier, 2 later. It doesn't go the other way. Okay, so it could be 2 from 2 to 3, right? From 1 to 3, from 1 to 2, from 1 to, wait, 2 to 3. And you'll see. So we need to draw that. Let's do that for a second. You see, it's a pretty short list. This covers about the first month of your class. Can you believe that? There's a lot to learn in here, but it's very doable. All right, so let's look at a process. Well, I could have horizontal, and that would be parallel to a flat level ground, right? And I could choose this. Now, watch this. Something's moving horizontally. Let's make that a ground. Da, 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 da. All right. And some object is wherever. It's here. And I say, what's its position? I don't know. It's right there. Okay. Then I could say, well, that's where I started my stopwatch. Now let me make a point. Some people might say X0. And I show you this in the book. Some books use XI for initial. And I'll tell you, I've seen it and seen it and seen it, where you think that's fine, but it's going to confuse many people. Okay, so the earlier or later is significant. I'm talking to the people that are teaching this class too. It's very significant what that does. To not say X0, but to talk about earlier and later, because you can relate any state as the earlier as long as you relate it to a later state. So I could call that XE. Now I'm just going to call it X1. But what's the number? What's the number? I don't know. You know, if I do, okay, I need to choose which way is plus. So that's my coordinate system. Now I'm going to choose this way plus, because it doesn't have to be to the right. Plus X. And then usually I'll put the units right next to it. Meters, which is a long step. It's about for me, from my ear to the into my hand. So meters. We'll use that quite often. 1 meter, you're going to see in chapter 2, is 3.28 feet. Those are things you're going to have to remember, put on a flashcard, commit them to memory, and then use it, and you'll own it. Okay, so if I say that was plus, then is this positive or negative? I don't know. Why? Because I don't know where I put my 0. You see, if I put my 0 here, if that's 0, then that's going to be to the negative side of 0, or negative. If, however, this is 0, it's to the positive side, right? So then it'd be positive. If I make that 0, then X1 is 0. It isn't always 0. And so the coordinates are critical. You can shift the coordinates, but the thing is physically there. It doesn't really care, right? You can say, I changed my coordinates on you. You're now in a negative position. Oh, darn, man, I'm so depressed. You made my position negative. Okay, so these choices you're going to get used to. This is going fast. This is an introduction. And then I do that. There's X1. Let's use color. And then let's go here, X2. So that means that somehow you went from 1 to 2. Now you could have done all kinds of things. These are just snapshots. All I have are these snapshots. If I have the movie, I could know what happened. For instance, maybe this person or object or dog or whatever, I'm only doing one dimension, so I'm not going all over, went this way and then back here. They still started and ended at the same place, right? Or maybe they went way over here and came back. Or maybe they went here, had lunch, and then keep going over here. Whatever. Anything could have happened between those states, right? But the truth of the matter is that the displacement from X1 to X2 is, and we're going to talk about vectors later, but it's from there. So this would be delta X 1 to 2. Now, maybe X3 is over here, or maybe it's just to make it interesting. If I can find my red pen, can't seem to. Maybe it's over here. Okay, x3. Now I haven't said where my 0 is. So is that plus or minus? It depends on where I choose my 0 to be. But independent of where I chose my 0, right? My displacement, my delta x from 1 to 3 is from here to here. Whatever happened, doesn't matter. You started here, you ended here. And you could have done anything to get there. Now, if you go like this, you're adding distance, right? You're getting more exercise, but the net result is the displacement. The distance we're going to see is along the path, which I use this. And for this, you have to know, you have to see the muddy footprints to count how many steps were taken. Displacement is just from there to there. From 2 to 3, it would be here, right? That's delta x from 2 to 3. I can't do 2 to 1 because that's later to earlier. 2 can be earlier though. That's why I don't like that initial. Oh, no. Now you could start at 0. You could go 0, 1, 2. I like to just start at 1. I think it makes more sense, but that's up to you. So from 1 to 3, yeah. From 1 to 2, yeah. From 2 to 3, yeah. Those are displacements. Now, notice this. Since I haven't decided where I want my 0, I don't know what my x's are, whether they're positive or negative. If that's 0, they're all negative. If that's 0, they're all positive. But I do know this. I know that this displacement is in the positive direction. I look at that, I look at that. That displacement is in the negative because I chose that already. I chose that to be plus. You could choose it the other way. But once you do, you got to show it. You're going to forget unless you lay those puzzle pieces out. This is just good work ethic. This is good, just a good approach to work that's critical for doing problem solving and engineering, biology, anything, science or applied science or anything in general. So I chose that to be plus. This is negative, that's positive. And that doesn't care where you put your 0. Now you can imagine that this applies for vertical motion as well, or motion along an inclined surface. Inclined surface is a very valuable example. So if horizontal is here, but this is a ramp or tabletop or even a screw where it's a curved ramp, right? It's a curved ramp. So this has lots of applications, just so you know. It's not only just an exercise. It's not only a simple case getting a little more complicated of applying this technique. It extends to interesting things. So again, I'm labeling my positions. Each of those positions, that's state 1. So that has a time 1, that has a time 2, that has a T1, and that has a T2, and so on. And so in a lot of these puzzles, you're going to have 3, even could be more, moments that you posit or states. Okay? So you've got time, then we've got the time between states from T1 to T2, delta T1 to 2. Let's write that. Delta T1 to 2. And then you've got the time between delta T1 to 3. And then you've got delta T2 to 3. And so there's a lot of combinations here, but it's not bad because you're laying the puzzle pieces out and they're not too bad. We're talking about time and position. Nice, simple processes, okay? But notice that I've chosen coordinates, I've shown states, and I've identified well-labeled, well-subscripted variables that will then go into my equations. If you just manipulate equations, people without this labeling lose sight of what they mean. And then it's just gobbledygook. And then you get a number, you don't even know what it means. And So this is critical because the math is actually often the easy part of it. This is setting it up. Now there's something else to this. What else do we need? Good news. You got time and change in time. You've got position and change in position called displacement. You also have distance, which is how many steps did it take to get from here to here? Well, that depends on your path. There's only a couple more things. And this will take you through a month. There's a lot to work with. What is it? Velocity. Velocity. Not the best. Let's see. It's better. Velocity. Velocity is your speed and your direction. So speed and velocity are not the same. That's the other thing. And you know, it's like anything. Learning subtlety of language. Blue versus turquoise versus teal versus aqua or whatever. At each of those states, we said, there's an earlier state. Which one? Well, it depends on what you want. So as you go through the problem, state 1 might be your earlier state. State 2 might be your earlier state. VE, and when I write a general equation, it's going to relate VE and VL. Earlier and later. That's the new notation. Okay, you won't find it in your book quite yet, but someday. V earlier can be 1, can be 2, can be 3. Then V later is any subsequent, V2, V3, V4. Right? And there can be a change in V. What would that be? Well, that would be the later minus the earlier. So the change in V from earlier to later, I use that E to L subscript. It's a little clunky, I know. It's going to save you, right? It's those little cookie crumbs, the little extras that's going to keep you. Oh, that's what that means. Oh, yeah, because you'll lose sight. You'll apply things where they don't go. It's just very common. Why? Because you completely lost the physics. And what are we learning? Physics, not math. You're applying math. You're getting better at math because you're using it. We love math, but we're applying it to physics. So math is broad, physics is very particular, okay? And so at each point, that's velocity. Now, how do I draw that? Well, I draw this, here we go, as a little arrow. If at x1 you are moving, right? You could be moving. I draw an arrow whichever way you're moving, and I say V1. X2 could be moving this way, and then you get back here. So I draw it with little arrows tangent to the path. We'll talk about that later. And then I'm just going to say real quickly, because we're about to zoom in class, that you also have acceleration. And I'll give you the quick thing on velocity is always in the direction that you're going. Even if you're traveling along a curved path here, then it's going to be tangent. Like if you hit ice, which way you would go. Velocity's, you know, here I went like this. Velocity is always tangent to the path. Displacement is always from 1 to 2, from 2 to 3. Notice that the displacement from 1 to 2 plus the displacement of 2 to 3 is the displacement from 1 to 3. You're going to get to that later in chapter 5. Also, acceleration. If the object is increasing speed, then the acceleration is in the direction of the velocity, like a push. Think of it, even though acceleration doesn't cause change in velocity, it just describes. But, and whichever way it is, if that's positive and my velocity is negative and I'm slowing, decreasing speed, acceleration is opposite. In this case, my example, acceleration would be positive while I'm decreasing speed. Acceleration is negative, increasing speed. When acceleration's with the motion, it's increasing speed. That could be negative. This is negative, increasing speed. Decreasing speed, they're opposite. This could be negative, this could be positive. This could be positive, this could be negative. They're opposite though, that means decreasing speed. Perpendicular is returning, okay? Distance and displacement are different things. This is along the path, I use D. and displacement. That's it. So you just draw your pictures, draw a bunch of pictures in chapter 1, get the hang of this, and it's very powerful.